Deep sir, am I audible?
Yes, audible. So, good morning. I think we can start.
Yes, I think yes, we can start.
Fine. So,
We can't start.
continuing from where Dr. Satendra has left, in this session, we will be majorly talking about the fundamentals of deep learning. And if we talk about the agenda, uh, we'll start from basics since I have got a feedback that many of the participants are not from computer science background. So, I'll try to keep it very basic. And starting from Maculopet neuron, MP neuron, we will go up to convolutional neural networks, and in between, we'll try to address all the aspects of fundamental concepts related to deep learning, how we train the models, what is a loss function, what is gradient descent algorithm, what is backpropagation. We'll take one of the case study of image classification using neural networks, and then definitely some insights into one of the popular deep learning network, which is convolutional neural network. The slides are adapted from various sources, which I'm highlighting here. Now, starting from uh, the inspiration of a neuron or inspiration of artificial neural network, artificial neural network. So it is basically inspired from the biological neuron. The processing, the way our human brain processes the information. Similarly, the artificial neural neurons are created. They are capable of taking decisions, and one of the key ingredient in these neurons is the activation function, which basically decides whether this information will be passed on to the next neuron. As you are aware, our human brain is a complex structure which contains a large number of interconnected neurons, and they basically come together to process information, take decisions. In the similar manner, uh, we have artificial neural network, which uh, performs the operations in the same manner in which our human brain performs the information. So basically, the artificial neuron is the basic computational building block of the modern deep neural networks, and we will see in the subsequent slides how the information is processed, how the decisions are being taken with the help of these neural networks. So the story started somewhere. Just give me a moment. Let me hide some of the information from you. Fine. So starting from the very basic McLopet neuron, this was one of the first stepping stone towards this modern AI. And you can see the timelines. Uh, what we can claim here is it took around 6 to 7 decades to come to this stage where we have generative AI, where we can say that yes, AI can perform tasks which can perform the tasks to a certain extent the way human perform these tasks. But the journey is very long, and I'll try to uh, summarize that journey uh, in this particular session. So starting from NP neuron, this was the first uh, efforts towards mimicking the human behavior. So Maculo, the neuroscientists, two scientists, Maculo and Fetz, they proposed a simplified computational model of the neuron. And the idea was there will be multiple inputs, and these inputs will be aggregated by the function g, and the function f takes a decision based on this aggregation. So it was very simple. Uh, Aggregation function is applied on the inputs x1 to xn. Based on the value computed by this aggregation, this will pass through a decision-making function f, and this decision-making function will apply some kind of thresholding on this aggregation. So theta here is the thresholding parameter, and we also call it the thresholding logic. The computation model is very simple. You have an input, the inputs are aggregated, they are passed through a function, And this function is nothing but a thresholding function. If this aggregation is greater than certain threshold, the output will be 1 or the output will be 0. So this was the basic about MP neuron. Now we can implement different type of gates using this MP neuron. First of all, let's see the AND function. Now suppose there are three inputs x1, x2, and x3. So to make the output of this AND gate as 1, we need all of these inputs as 1. So that's why the threshold here is 3. However, in the case of OR function, if any of the input is 1, the output will be 1. So in that case, the threshold here will be 1. In the case of, similarly, we can implement other gates demonstrated here, like NOR function or the NOT function on the right hand side. You can see the input, the threshold is 0, and then you can get the output whether it is 0 or 1. If we delve more, if we take a closer look on the OR function implementation using the MP neurons, you can see here we have drawn a decision boundary. On the x-axis, we have input x1, and on the y-axis, we have input x2. Now, as we have already discussed, we know that in OR function, if either of the input is 1, we will get output as 1, otherwise it will be 0. So if both the inputs are 1, then also we'll get output as 1. Fine. So basically, you can draw a decision boundary on this feature space where this decision line on the right hand side, you will have output as 1. On the left hand side, the output will be 0. So this is a decision boundary of this OR function. Similarly, we have AND function. So in AND function, this decision boundary will cross the coordinate 1, 1. On the left hand side, any combination of x1 and x2 will give you 0 output. However, any inputs corresponding to this decision boundary line or the right hand side will give you output as well. So in this case where we have two inputs, this AND function implementation of MP neuron will have a threshold as 2. This could be the case where we have three inputs. So in case of three inputs, the decision boundary will be of different shape that will be in 3 dimensions. As you can see here, for the OR gate, the decision boundary will be a surface. Now there are certain limitations of the MP neuron. As of now, you have seen that we are just taking the Boolean inputs, 0 or 1. How about taking non-Boolean inputs or the real inputs? Because the problems which we are going to deal with, they will be having real inputs as well. How about this threshold? How do you decide this threshold? In this example of this implementation of weights, we have hand-coded the threshold. So that's another limitation here. Now, the third thing is whether these inputs are equal, whether they have the same weightage. There might be possible that one of the weight will get more weightage, one of the input might get more weightage, other inputs might get lesser weightage. So why can't we assign weights? And weight signifies the importance of the input. Right? Now, in the example of this gate implementation, all these were the linear ones. The decision boundaries were linear. How about the implementation of XOR gate? You cannot have a linearly separable boundary. So how to implement them? What about the functions which are not linearly separable? How do we implement them with the help of MP neuron? So though MP neuron was the stepping stone towards implementation of neural networks, but yes, there were limitations, a lot of limitations, and that gave birth to the concept of perceptron in 1958. Where Frank Rosenblatt and Frank Rosenblatt proposed the classical perceptron in 1958, and also, Minsky and Peppert in 1969. They also refined this concept of classical perceptron. Now, in comparison with the NP neuron, perceptron introduced the numerical weights for each of the input, and they also proposed perceptron has a systematic methodology of learning these weights, and these weights basically tells you which of the input has more importance. We'll take some examples here how these weights plays a significant role in solving some problem. So it was more general computational model in comparison with NP neuron, and also it addressed the problem of known Boolean inputs. So basically, perceptron can also take known Boolean or real inputs. Now here, if we see mathematically, on the top right-hand side, you can see the aggregation of weighted inputs. Why weighted inputs? The inputs are being multiplied with the corresponding weight. That's why the aggregation from I1, I is equal to 1 to n. Let me take the marker. So the aggregation of these weighted inputs, Wi multiplied by xi, I is the index for the input. If it is greater than the threshold theta, then the output is quite similar to the NP neuron. However, we have introduced the weight for each of the inputs Wi. And another thing is this xi can be non-Boolean. And the other case, y could be 0 if this weighted aggregation of inputs is less than theta. Now, another way of representing this is why can't we parameterize this theta? Take this as 0th weight and take a fixed input x0 as 1. So basically, you can also write it as if the aggregation of this wi and aggregation of this weighted input minus theta is greater than 0, then your output y will be 1. And similarly, the other output 0. Now, the more accepted convention could be this index of input can start from 0, where the 0th input is fixed, which is 1, and this 0th weight is minus theta, and theta is the threshold which we have considered earlier. Right? So W, there is a question here. What does W represent? So W is the weight. As I was telling you, weight means the importance of each of the input. So suppose we are going to give more importance to x1 while deciding the value of y, we will assign larger value to w1. Fine. And if a certain input has a lesser importance while deciding the output y, in that case, the corresponding weight will have very less value. That means we are giving lesser importance to that particular input. I hope that out is clear. Can x can be any real input? Yes, x can be real. Now let's take an example here. The example is suppose based on certain parameters we want to decide whether we would like a particular movie or not, or whether a particular audience will like the movie or not. And suppose we are taking three inputs x1, x2, and x3. X1 is if the actor is Shah or not. Second input if the genre is thriller or not, and the third one is if the director is Karan Johar or not. So these three inputs, based on these three inputs, we will decide whether the audience will like this movie or not. Now suppose, what is the importance of weights here? Let's see. Suppose there is a hardcore fan of Shah Rukh Khan while watching the movie. So in that case, the weightage, the weight W1 will have very high value. It doesn't matter whether it is thriller or who is the director. For that particular audience, yes, which input matters most is the input x1. So the model will give, I will tell you how we train the model. The model will give very high weightage or very high value to the weight W1. Right? I hope the confusion is clear. Let's say there is let's say there is a movie buff. The movie buff can watch any movie, right? So now you have seen the importance of W1, W2, and W3. This is relevant to X1 and X2 and X3, the inputs X1, X2, X3. How about W0? That's the threshold theta. So this threshold will be very low in case the audience watches a lot of movies. This threshold theta will be very high in case very few audience watches the movie. So I was giving you an example of the movie buff. It doesn't matter who is the actor, what is the genre, who is the director. Movie buff will watch any movie irrespective of these inputs. In that case, the value of theta or the value of W0 will be very low, as close as 0. However, if the audience is very choosy, very restrictive while uh, deciding whether you have to watch a movie or not, in that case, this threshold, the value of this W0 theta will be very high. In other words, we call this W0 as bias because it represents some kind of bias. So while developing a perceptron-based model, we learn all these parameters like W0, W1, W2, and W3 based on the past viewing experience of the past data which we have. So simply comparing NP neuron and the perceptron, in NP neuron, we don't have any known Boolean inputs. There's no weight mechanism. However, in the case of perceptron, we have weights and we also have a learnable parameter which is the threshold or the bias. Now coming to the OR function example here, you can see this is the truth table for the OR function, two inputs x1 and x2 and the output. And if any of the input is 1, we'll get output as 1. So this can be represented in terms of this weighted aggregation and the equation related to it. There could be multiple solutions for these inequalities. One could be taking the value of W0 as -1 and put the inputs as 1 point. There could be various other solutions possible. Now, since there are multiple solutions available, and what we can do is multiple solutions available. That means there is a decision boundary. On either side of that decision boundary, we have output as 1. On another side, we have output as 0. So what we can do is we can find out errors for a particular decision boundary or the line. Suppose we have fixed the threshold W0 as 1, minus W0 as 1. And let's try different values of W1 and W2. Let's consider W1 and W2 as -1 and -1. You can see this particular line represents W1 and W2 as -1. In this case, you can see that all the possible combinations of x1 and x2 are on the right hand side. There are 4 possible combinations of W1 and W2. One of them is the correct one. However, the other 3 are the errors. And similarly, if we take W1 and W2 as 1.5 and 0, there will be error as one of the point will be the error. This particular one. And finally, we have another combination 0.45 and 0.45. In that case as well, there will be 3 errors. So basically, the idea here is to find out the best values of W1, W2, and W0 so that we have 0 errors. And this whole process of finding the best values of W0, W1, W2 for the weights is training on that. So that's the concept of error surface. So for different values of W1 and W2, while keeping W0 as fixed, we can plot an error surface. And on this error surface, wherever there is minima, those values of W1 and W2 will be the best values for the model. Now, in this case of perceptron here, what we have done is we have again considered a threshold. If the weighted aggregation of the inputs is greater than the theta, then we say that the output will be 1. And if it is less than that theta, we'll say the output is 0. Let's take that example again, the movie example again. Suppose we have considered the bias, the W0, as minus 0.5. What if the weighted aggregation of the inputs W1, W2, and X1 and X2 comes as 0.49, which is less than that threshold? We will say that we won't like that particular value. And if the rating comes, the aggregation, let's take a simpler example here where we are taking only one input as IMDb rating. So there is one input X1, there is one weight, corresponding weight as W1, and there is a bias which signifies the threshold. If the weighted combination of X1 and W1 is greater than that bias W0, then we will say, yes, we will like that movie. Otherwise, we will dislike this movie. So in this case, if the weighted combination of X1 and W1 is 0.49, we'll say we dislike this movie. And if it comes as 0.51, we say we like that particular movie. This is very harsh. Why can't we have a smooth kind of transition? And see here, in the case of this thresholding behavior, you can see this graph here. There is a sharp change at W0, which is not as the practical behavior. So the perceptron function is a step function, and there is a sudden change in the decision when this process, the weighted input or weighted aggregation process the threshold. So for most of these real-world applications, we expect a smooth decision function, which gradually changes from 0 to 1. Not like this one, where it is there is a sudden change in the decision from 0 to 1. So that, I mean, the sigmoid neuron provides that kind of output to us, where the transfer function, we also call it logistic function, which is in terms of the exponential. So it is 1 upon 1 plus exponential of this weighted aggregation of the inputs. Now we say that we see that there is no sharp transition around this threshold, and there is a smooth transition from 0 to 1 in the output. So instead of directly saying whether we like or dislike the movie, we will get a probability of liking the movie. So basically, this sigmoid function, this logistic function will give you a probability of output, 0.6 or 60% probability of liking that movie. And then we can apply certain mechanism to decide what probability we consider as 1 or what probability we consider as output as 0. This is just the depiction of what we have discussed here. In perceptron, we have hard threshold. However, in sigmoid or a logistic neuron, we have a smoother decision function, or we also call it activation function. So in the case of perceptron, it is not smooth, it is not continuous, and the very important part is not differentiable. As in the later slides, we will see how do we train these neurons, how do we train these neural networks. While training, we compute the gradients. We compute the gradients of the loss function with respect to these parameters. So it is very important that these functions are differentiable. So in contrast to perceptron, the sigmoid neurons are smooth, continuous, and differentiable. So this is just a depiction of the complete perceptron. You have inputs, x1, x2, and so on. There are corresponding weights. There will be aggregation of these inputs. So basically, it's a weighted linear combination of the inputs. And then we apply certain kind of non-linear activation function, which basically decides whether this input will be activated. This output will be activated based on the received input, or it will be deactivated. So of course, there is a bias term which comes into picture at the aggregation stage itself. Now, why do we need these activation functions? And why do we need these non-linear activation functions? For all the practical, the real-world problems are non-linear in nature. So while taking decisions, we need some kind of non-linear function for the mapping of input to the output. So these activation functions are here to introduce the non-linearity into these neural networks. You can see this example here. You have to build a neural network which can differentiate between the blue and yellow balls or yellow dots. You need some kind of nonlinear mapping function. And that's the role of activation function here. So basically, the linear activation function produces linear decision boundaries, and the non-linearity is needed to learn the complex representation of the data. There are some of the examples of activation function. Sigmoid we have already seen just now, and then the rectified linear unit, which is one of the parameter of success of these deep neural networks. The problem with sigmoid type of activation function was vanishing gradients. As I was telling you, whenever we will be training these models, we will be computing gradients. So in case where we are using sigmoid kind of activation function in the network, there's a problem of vanishing of the gradients, and which basically limits the learning power of the network. However, in the case of rectified linear unit, you can see this looks very linear kind of activation function. However, it is a non-linear, and it solves the problem of vanishing gradient. Now, the third or another important aspect is the bias. So you have seen that bias W0. This bias basically helps us in controlling the value at which this activation function will trigger. You can see that the theta was the parameter there. So if the aggregated input is greater than that theta, then only the output was triggered. So basically, this bias helps us in controlling at what value this activation function will trigger. And if we don't apply this bias in the network, the model will train over point crossing through origin. and which is not as per the real world scenario. So with the introduction of this bias, we made this the whole model very flexible and generalizable. You can see three of the examples, the different sigmoid curves with different bias values. Now coming to typical machine learning setup, we must have studied in the previous lecture how the machine learning model works. So given it's a typical supervised machine learning type of test case where we have data input x1 and the output y1, and there are n such data points. The task of the model is to find out the relationship between the input x and the corresponding output y. In the previous lecture, you must have studied that you know the input, you know the output, but in machine learning, you need to learn this function of mapping between input x and y. So in the case of the sigmoid activation function, you can see here, this could be your output, y cap, and this could be the relationship between the input and the output. This could be another way, and this could be another mapping function. So it could be any of the function. Different type of machine learning algorithms are there, and they have different mathematical functions to map the input and to the output. And that particular mathematical function contains different parameters. And the task of training a machine learning model is to learn the best parameters of that mathematical function so that it fits the given data. So W is the parameter in this case here, which we need to be learned from the data. This learning algorithm, finding the best value of W or other parameters, is we get it through the learning algorithm, like gradient descent, and there are other ones as well. Specifically in the case of neural networks or deep neural networks, we use gradient descent algorithm. And then we have optimizers which help us in implementing. Yeah, I have a question. Just give us some example of multi-layer perceptron. I'll take one of the examples here. I'll take two test cases, use cases of neural network in classification. Thanks. And then we have an objective loss or error function. I think you must have studied these terms in the previous lecture. So the whole objective of training a model is minimizing this error function. Now, in the case of the movie example, input is the name of the movie, or the features. There will be different features. There will be different inputs corresponding to this movie, and there will be output like or dislike. And then we do the whole machine learning setup for this, solving this particular movie example problem. How do we learn these parameters? What mechanism, what algorithm we use to learn the parameters of the model? You name any of the machine learning model has different parameters. Now, since we are sticking towards deep learning, fundamentals of deep learning, we'll talk about the neural network aspects. So while learning these parameters, what will be the input? Suppose we are considering a supervised machine learning here. So we will have labeled data. We'll have n number of pairs of input and the corresponding label, xi and y. What is your training objective? Finding the best value of the weights and biases. How? By minimizing the loss function. And what is loss function? How do we define this loss function? So loss function is nothing but it's comparison, this is one example of the loss function where uh, mean square error. This is mean square error function where you are finding the difference between the expected output because you know what your model should give as output for a particular input. So what do? You pass on an input xi to the model, apply that function f. This f is nothing but the machine learning model or the neural network. This model will give you certain output, which we define as f applied over xi. Ideally, the output of this model should be equal to the label which we are providing during the training. So this difference between the expected output or the ground truth output and the output of the model is defined as the loss function or the objective function. And what are the variables here? What are the tunable parameters here? That's the weights and biases, which constitutes this function f. So if you change the values of this w and b, the output of this model will change. And our whole objective is to bring the output of this model as close as possible to the expected output. So let's drill down more on this one. Suppose we train the network with x and y. These are the two data points which are given to us. For 0.5 input, we get 0.2 as output. For 2.5 input, we get 0.9 as output. Suppose this is certain model, and this is the training data which is provided to us. So at the end of the training, our expectation is to find out the weights and biases in such a way that if we give 0.5 as input, our model F should give us output as 0.2. And if we provide input as 2.5, our model should give us the output as 0.9. So this is what the training means. Finding the best values of W and E so that our model starts giving the correct output or the expected output. And how do you know the expected output? Because you have labeled data. You are performing a supervised machine learning. I got a question, what are W and B? So W is the weight and B is the bias. As I told you earlier, in the neural network, when we were discussing these perceptron or the sigmoids, you can see here we have weights corresponding to each of the inputs, W. And then this W0 is nothing but the bias. So now, how do we train? Let's have a look like how can we achieve or learn these parameters in a layman way. Suppose this is your model, this is your function f, and this is nothing but a sigmoid neuron in which the output is determined with this transfer function. So can we try to find out the values of w and b, the weights and biases manually? Let's try some random guesses. Suppose randomly we pick w as 0.5 and bias as 0. Fine. And then we plot this sigma x here. And these are our two data points. If you give 0.5 as input, our expected output is 0.2. And if you give input as 2.5, your expected output is 0.9. But this particular sigmoid with values w as 0.5, bias as 0 is nowhere closer to these two data points. Ideally, it should cross these two data points. So we can compute the loss function. And how do we compute the loss function? We find out the square of the difference between the expected output and the model output. And what is the expected output, since there are only 2 points which we are considering here. So y1 minus fx1 square plus y2 minus fx2 square. Y1 in the case of input as 2.1, 2.5, your expected output is 0.9. This is what is the difference here, and this is what the difference here. And how do you compute this f? F is given by this formula. This is your model here. You are using a sigmoid neuron. So if you compute the value of this sigmoid function for x as 0.5 and w as 0.5, bias as 0, you will get a certain value for this particular input, and similarly you will get a certain value for input as 2.5 and bias as 0 and weight as 0.5. So this is error. This is the error if we consider w as 0.5 and bias as 0. But what is our aim? What is the aim of training is to minimize this loss function. This loss function should be as close as 0. We need to find out the best values of w and p, then only it will become 0. So let's have some more guesswork. For values of w as minus 0.1 and bias as 0, we have this loss value. And by hit and trial, what we have seen is for the value 1.78 for weight and minus 2.27, the loss function is 0. We are able to find out the best values of W and P. This looks very simple, but no, this is not. You have a very larger space for W and P. Sampling a particular value for finding for which the loss function is 0 is very typical. This example, we are considering there are only 2 parameters W and P. Consider the networks, consider the deeper networks where we have millions of parameters. Consider the Chat GPT or DeepSeek where we have billions of parameters. So I got a question that finding the values of W and P is hit and trial. No, this is just, I'm giving you an example so that you can understand how typical it is. This was just an example by how we are finding the value of W and P by hit and trial. But in actual, no, we cannot find out the values of these parameters by hit and trial. There is a proper mathematical way to find the values of these parameters. So learning parameters. So if we have, since we have only 2 points and 2 parameters W and P, we can easily plot error surface here, and then we can find out the minimum value of this L, and for that minimum value, the optimum parameters will be W and P. But that's not the right way. You can see here for this case, for W is 0.5 and bias as 0, this will be the sigmoid function, and this will be the error here. For this case, where W is minus 0.1 and bias as 0, this will be the point on the error surface. And finally, you will get a point where you have minimum error, and which is this particular sigmoid is crossing through these 2 points, and that's the particular curve. And this values of W and P gives us minimum value of error on the error surface. Now, instead of having a single output perceptron, we can have multiple output perceptrons as well. So corresponding to each of the input, we will have corresponding weights for that output perceptron. So this is one layer neural network. As of now, we were just talking about a perceptron or a sigmoid neuron, which is just one neuron which takes input, aggregates the information, and gives you output. Now what we can do, we can interconnect these neurons. Suppose there are two neurons here, Z1 and Z2. Similarly, we can have n number of neurons and interconnect them. So that's how we constitute a one-layer neural network in which you have input, one hidden layer, and then the output layer. And the advanced form of neural networks is the deep neural network. That's why we call it deep learning. The term deep means the number of hidden layers, the size of the network. If it is deeper network, that's why we call it deep neural network. And from where the term has come up, deep learning. Am I audible clearly? Can someone please confirm if I'm audible? Okay, fine. I have received responses. Most of you have confirmed that. Yes, I suggest all of you to please increase the volume of your system. Fine. Those who are not able to listen to me, because most of the responses I have received here as audible. So those one or two responses which I have received, they said they are not able to. I mean, the voice is low. I request all of you to uh, please increase the volume of your system. I'll try to be little louder. Now, coming to one of the typical example of neural network application. Suppose we want to estimate a housing price. So we want to estimate a housing price. Now, what could be the inputs when you are trying to estimate the housing price? For simplicity, let's take a three input model: the number of bedrooms, the area, size of the house, the locality of the house, and then let's construct a neural network which gives you as output price of that particular house. So how do we build this model? How do we train this model? And then how do we test this model? Let's talk about it. You can see here is you have an input layer, you have a hidden layer, and then you have an output layer. What is the task of this hidden layer? What is the task of this hidden layer? So these hidden layers basically compute more information from the input. Whatever input we are providing to this network, we compute more information, we extract more information from this input. This input might be very good. So the task of these hidden layers is to extract more and more information. Now imagine in deep neural networks, we have large number of hidden layers. The network is very deeper. More the number of these hidden layers, the network will be able to extract more and more information from the input. So now coming back to training this model, so what do? We basically collect a large amount of data, large amount of labeled training data, since this we are considering as supervised machine learning. So what do? Based on these three inputs, these three parameters, we know what is the price. We do a survey, make a sample report, make an Excel sheet where you have three inputs and the corresponding price of that house. Now, what is training? What does training mean? Training means we will provide these inputs one by one to this model. We know the expected price of or expected output for that corresponding inputs. We randomly initialize the weights and then find out the output of the model. Suppose for this first combination with the random initialization of the weights, we get certain output. Suppose this output is 20 and the expected output is 30. there is some error or there is some loss. Now, the objective of training this neural network is to adjust the weights and biases of this network so that the output of this model is close to the expected ones. Now, we provide the second input and see what is the output of this model and compare it with the expected one and calculate the error. For simplicity, what I have done here is I have just uh, find the difference between the expected output and the output of this model, computed output of this model. There could be different type of loss functions or error functions or objective functions like loss entropy, mean square error, and other ones as well. So based on what type of problem you are trying to solve, we formulate that kind of objective function. Now this is the whole summary flow. You give these inputs, you find some outputs, compare them or compute the loss function, minimize that loss function by adjusting the weights and biases so that this model starts giving the output as the expected ones. Fine. So what I do here is let's take a 2-minute break and then we'll assemble again. So just let's have a bio break and we'll assemble here in 2-3 minutes. Yeah, welcome back. So, am I audible now? Can someone clarify? I mean, it is whether it is clearer than the earlier one. Okay, fine. So let's continue where we stopped. This is the whole picture here. We provide the training data. We know this training data is the labeled one. The whole objective of training is to minimize this loss, uh, and loss is calculated between the output of the model and the expected outcome of the output of the model. And we know the expected output because we have labeled data with us. Now, uh, some more discussion on the feed-forward neural network. You can see here we have n-dimensional input to this feed-forward neural network and how the information is being processed through this feed-forward neural network. As of now, we have just taken a simple example. Now let's have a closer look from a mathematical perspective here. What we have taken here is there is n-dimensional input vector, and suppose this network contains L-1 hidden layers, and so we are considering L as 3. So there are 2 hidden layers here, and each of them has n neurons, and n is equal to the number of inputs. So that's why it is a feed-forward neural network. And finally, there is one output layer, and which will contain k number of outputs, and this k is nothing but the number of classes. So basically, this is a typical classification model in which we are taking input, passing these inputs through the hidden layers, and finally we have an output layer. This output layer contains number of neurons equal to number of classes. Now each neuron in the hidden layer and the output layer, each of the neuron can be split into 2 parts. As we have seen earlier, the first part is the aggregation part, and the second part is the activation part, which we have already seen. We also call it pre-activation and activation. So each of the neuron, you can see this is divided into 2 parts, and it is performing 2 tasks, as you have seen earlier in the case of perceptron and the sigmoid neuron, where we have discussed it in detail. The pre-activation is basically aggregation of the information. So basically, in pre-activation step, we are aggregating the information. So it's linear weighted combination of the input. And once this aggregation is done, this is passed through the activation function, which is the second step in this neuron, and that will give you the output. So the pre-activation here is AI, and the activation is HI as vectors. So the input layer can be called as the 0th layer of this neural network, and the output layer can be called as the Lth layer of this network. Now these weights, what will be the dimension of these weights? As I was telling you, for a particular neuron, we have seen earlier, for a particular neuron, you will have weights corresponding to each of the input. So suppose for the first neuron in the first hidden layer here, it will receive all these inputs n, and for each of these inputs, you will have corresponding weights from W1 to Wn. Similarly, for this particular neuron, it will also receive inputs from all of these inputs, x1 to xn, and there will be corresponding weights, and so on. And each of the neuron will have one bias. So what will be the dimension of these weight matrix here between the input layer and the first hidden layer? It will be R n cross n, because there are n inputs and there are n neurons in the first hidden layer. So each of the neuron in the hidden layer is connected to each of the input, and if it is connected, that means there is weight associated with it. And in the last layer, since the output layer has only k neurons and the last hidden layer has n neurons, so the weight dimension of the weight matrix will be n cross k. And there will be only k biases corresponding to each of the neurons. However, in the case of these hidden neurons in these hidden layers, the dimension of the bias will be n. Now, how the information is being processed? The pre-activation at layer I the pre-activation here at layer I is computed as AI of X is equal to the bias, BI, this bias, plus the weight multiplied by the output of the previous layer. So let's consider this particular layer here, because here we have this H inputs as well. So consider this particular hidden layer and then see this formula again. You have pre-activation, this A2X. This A2X is computed as the bias plus weight being multiplied with the output of the previous layer. So what is the output of the previous layer, which is H1. So this output multiplied by this weight mechanism, this weight matrix, and the bias is added, then we get this pre-activation. This is nothing but the aggregation, the linear weighted combination of the input, which we have seen earlier. And then at the activation, we find out this H2, and H2 is nothing but the activation applied over this pre-activation. This is what we are getting. So I hope this is clear. Very simple. You do the linear weighted summation, add the bias, and then you get this pre-activation. And this pre-activation, the aggregated information is passed through an activation function G, and then you get the activation. So this G is called as activation function. This could be sigmoid, this could be a rectified linear unit, this could be 10H, fine. And at the output layer, you can have the activation function is same as the hidden layer, or you can use a different one. Based on the application, you can choose what kind of activation function you want to apply. So this is what the feed-forward neural network does, how it processes this information. Now, whenever you will be studying any deep neural network, this will be the basic phenomena which will be used. This will be the basic information processing route or forward propagation which will be used in these deep neural networks. Now, coming to our machine learning setup, what you have here, you have data x1 and y1, the labeled data, and such data points. What does your model do now? This is very important to notice. What does your model do now? Coming to the first layer, the input layer, and the first hidden layer, what is being done here? This weight matrix being applied to the input vector plus the bias B1. This processing here. You are computing A1, and how you are computing A1 by aggregation of these inputs, linear weighted combination of these inputs. That's how you get A1. So basically, W1 multiplied by the input vector xi, and the dimension of xi is n. Dimension of W1 is n cross 1, and the dimension of bias is n B1. And then on this pre-activation A1, you apply the activation function G, and you get the output H1. Now this H1 is again multiplied with the weight matrix W2, and the bias is being added, this B2, and it is passed through an activation function G. Here you have got this A2. Further, from A2 you have got H2 by applying this activation function G. Further, this is being multiplied by this W3, the weight matrix. This bias is added B3. And since in the output layer we are using a different activation function O, which is being applied on this input. So what are the parameters? And that is how you get the output of this model. What are the parameters? All the weights and the biases. So W1 to WL, L is number of layer, biases B1 to BL, and there are 3 layers we are considering. Now, how do you find out these values of W and weights and biases? there is an algorithm called gradient descent algorithm, and we use back propagation with gradient descent for training this model. This we will see in the subsequent slides. And what is the objective? What is the task which we are trying to solve in feed-forward neural network? We are minimizing an objective loss or error function. And what is it? This is this y cap ij is your output of the model, minus y ij is your expected output, and this is one type of loss function we are using, and we are trying to minimize it. This L theta we are trying to minimize. And how do we minimize? We find out the best values of these weights and biases. Now there is a mathematical way to do it. Let's consider two parameter problem W0 and W1. We have seen this kind of error surface earlier. The whole objective is to minimize this J, W. J is the loss function defined in terms of these weights W0 and W1. So we can plot an error surface. And this error surface, we have to basically find out the minima on this error surface. And that we do with the help of gradient descent algorithm. The term gradient is very important here. We will compute gradients of the loss function with respect to these parameters while optimizing the loss. So basically, that's the glimpse of gradient descent algorithm. We randomly pick the initial values of W0 and W1. We compute the gradient of the loss function which we have formulated. Here in this case, this was the loss function. This was the loss function. Take small steps in opposite direction of this gradient. So basically we compute the gradient of this loss function with respect to the parameters, the weights and biases. With each of these parameters, that means with each of these weights and the biases, then we update these weights and biases by taking a small step in the opposite direction of the gradient. So the new value of the weight will be the previous value minus neta and the gradient of the loss function with respect to that weight. And neta is nothing but the learning weight. How fast you learn. If the value of this neta is high, that means the learning rate is also high, but there is a trade-off. So this is a hyperparameter of a model, which we have to carefully decide while training these models. And all these steps are repeated until the convergence, where we have minimized this loss function with respect to these model parameters. Now, how do we define this algorithm mathematically? So randomly initialize the weights and biases. We define number of iterations for which we will compute. As I was telling you, repeat until convergence. So we can also define next number of iterations for which we will conduct this training of the gradient descent algorithm. Now, what does this algorithm do? Till the max iteration, what we have to do, we have update the value of these parameters, weights and biases. And how do we update? We move in the opposite direction of the gradients. This del Wt is nothing but the gradient of the loss function with respect to the parameter W. Similarly for bias. And of course, we can define it in a matrix format as well. We can have this theta 0 as the weights and biases, and consider this theta as one parameter, and then optimize the value of this theta. Now, coming to our feed-forward neural network, where we have large number of parameters. As you have seen, there are three layers, and there are n number of inputs, and correspondingly, the dimension of W1, W2, and W3 is n. W1 and W2 is n cross n. However, the dimension of W3 is n cross k. Now, what we have to do is in this, try to imagine the computation which we require for training a larger model. If we have to compute this gradient, that means we have to compute this gradient of the loss function L theta with respect to each of the parameter in this network. So how many parameters are there? N cross n here, n cross n here, n cross k parameters here, and of course these are k, n, and n. These many parameters, for corresponding to these many parameters, we have to compute the gradient. Right? So that's the amount of computation we require. And here we are using only a 3-layer neural network. Consider where we have large number of layers in deep neural networks. What amount of computations we require? That is the reason we need high-end computation hardware. And you must have heard about graphical processing units, GPUs. That's why we need graphical processing units. They help us in doing these computations in parallel and increasing the speed of these computations. Now, let's extend this del theta. This del theta can be represented with respect to the gradient of this L theta with respect to each of these parameters. As I was telling you, we have to compute that since we have to update each of the weight W, W weights and biases. So we have to compute the gradient with respect to each of these weights and biases. You can see here this W1, W2, and WL minus 1. The dimension is n cross n. However, the weight matrix in the last layer is of dimension k cross n. Similarly, these biases, the biases in the earlier hidden layer, except the last one, they are of dimension n. However, the biases in the last layer are of dimension k. So we have to compute all these values, these gradients of the loss function with respect to all these weights and biases. Now, coming to back propagation, once we have computed them, how do we take help of back propagation for training these models? Suppose we want to focus on this particular weight W1, 2, and to learn this weight, we need gradient descent, and we need a formula, or we need to compute the gradient L theta with respect to W1. So this is the gradient of the loss function with respect to this particular weight W12. How do we compute it? We take help of back propagation. We back propagate the error into the network and to compute these gradients. So if we just consider this particular leg here, the input, one, the corresponding weight, the pre-activation, activation, and then again multiply it with weight, pre-activation, activation, weight, and the output. So how can we find out the derivative with the help of chain rule? So if we want to find out the derivative or the gradient of this L theta with respect to this weight W111, what we can do is we can find out the gradient of this loss with respect to y cap, then gradient of this y cap with respect to this pre-activation, then with respect to this, and so on. So we can apply this chain rule for finding this derivative of this loss function with respect to the weight which is deeper in the layer, or which is at the start of this neural network. So how do we define it? We can just compress this chain, and that is how we can compute the gradient with respect to this W11. So this is L theta, gradient with respect to H11, this activation, and the gradient of this H11 with respect to W1. And similarly for other weights. Now, let's have a closer look on this one. Suppose we get a certain loss at the output and we try to figure out who is responsible for that particular loss. It might be possible that certain parameters might be contributing very high loss. So we need to find out which of the parameter is responsible for this high loss. So what do? We talk to the output layer here and say that you are not producing the desired output. That's why we are getting very high loss. Since loss is computed here, we consider these output neurons as the main responsible factors towards this loss. But what does these output layer says? They say that I'm just doing my task. I'm just processing the input which I'm getting here. So I take the responsibility for my part, but please understand that I'm only as good as the hidden layers and weights below me. So this output layer says that whatever input I'm getting here, I'm just processing that. So there might be some responsibility associated with me while deciding this loss function. But yes, the others are also equally responsible. The weights and biases below this output layer, they are also responsible for this loss function. Because if you see this formula, this y cap is computed as activation function O, the output activation function, applied over this activation at previous layer. So this activation at the previous layer is computed in terms of activations or pre-activations and weights in the previous layers. Okay. So further, we ask the previous layers, what is problem? What's the problem with these weights in the previous hidden layers? So basically, this WL and PL take full responsibility, but HL says, well, please understand that I am only as good as the pre-activation layer. And the pre-activation layer in turn says that I am only as good as the hidden layers and the weights below me. And so on. So this becomes a chain. So we continue in this manner and realize that responsibility lies with all the weights and biases in the network. So what's the idea here? Instead of talking to them directly, it is easier to talk to them through the hidden layers and output layers. And that is what this chain rule allows us to do. You see the example here. This is the example where we talk directly to the weight. So instead doing that, why not talk to the output layer and then talk to the previous hidden layer and then talk to the previous hidden layer and now talk to the weight. So that is how this chain rule helps us and the back propagation helps us in finding out these values. So this is just a glance of gradient calculation and the back propagation. What do? We provide the inputs at the corresponding activations for input layer. Do the feed forward for each layer, compute the output and the activations. Compute the loss and the gradients. Compute the loss and the gradients at the output layer. Back propagate, that means use the chain rule and compute these gradients with respect to the each variable in the layer. So this back propagation is helping us to calculate those gradients with respect to each of the variable in each of the layers. Instead of directly jumping to individual weights, we follow the chain rule while computing the gradient corresponding to a particular weight or the bias. And then output, the gradient of the cost function with respect to learnable parameters are used to update the weights using gradient descent. So this is a little tricky one, But there are algorithms, the optimization algorithms like Adam optimizer. There are n number of optimizers available, which helps us in training these models, implementing these training models like probability models and uh, methodologies and gradient descent algorithms. Now, not going much more into detail, let's take one of the use case. I think we are running out of time. I need to expedite it. So let's take one of the simple example how we can do binary classification or classification of an image. There is a popular dataset MNIST, which is for digit classification, and the size of each input is 28 cross 28. Now, how do we feed this 28 cross 28 image to our neural network? Let me explain it here. Fine. What do we do is this 28 cross 28 image is vectorized in the format 1 cross 784, and this 1 cross 784 is the input to the neural network. So basically your input layer is of dimension 784. There are 784 neurons. Each of the pixel is going to be input to your neural network. I'll demonstrate it in subsequent slides. And then we will have the weight matrices and biases in the subsequent layers. Let's take an example here. This is your 28 cross 28 image. That means there are 784 pixels. These 784 pixels goes as input to this neural network. This is the input layer, x1 to xn, where n is 784. In the first hidden layer, we have 16 neurons. In the second hidden layer, we have 16 neurons. And in the output layer, we have 10 neurons because there are 10 classes from 0 to 9. Because there are 10 digits which we are classifying. So this particular data set is MNIST data set, which is handwritten data set. And we are demonstrating how this neural network helps us in classifying these handwritten digits. Now, we have provided the input, 1 pixel as input. I mean, all of the pixels as input to this neural network. What is the role of these hidden layers? As I was telling you, these hidden layers are helpful in extracting information out of the input. Now, this is raw input, 784 pixels. What meaningful information you can extract from these inputs? That is the task of these hidden layers. So basically, they will form the patterns, they will form the structures from this input, which is meaningful in deciding what kind of digit it is. What these hidden layers are doing. These hidden layers are basically constituting or extracting information from these pixels. So this digit 9 can be represented with combination of this. Similarly, 8 can be represented with combination of this. So what these hidden layers are doing, they are basically computing the constituent part of each of the digit. Similarly, this particular hidden layer is computing the subparts of this digit from the raw pixels. Now, one important uh, point to notice here is some of the neurons are white. That means they are activated, and some are not activated. So how this information is being processed? There will be weights here, right? These weights will be multiplied with these inputs. There will be aggregation here, and there will be an activation being applied over. So only the neurons will be activated where the weighted sum is passing through. I mean, the linear weighted combination of these inputs are passing that threshold, or they are igniting that activation function. So only those neurons will be activated. In this case, only these two neurons are activated, and finally, they are classifying it as digit. only activate meaningfully when weighted sum is greater than certain bias. And how do we decide? I mean, this bias is also learned. Now, if you consider the number of parameters, how many, what will be the dimension of the weight matrix here? It will be 784 cross 16. Here it will be 16 cross 16. Here it will be 16 cross 10. So those many weights are there. And how many biases? 16 neurons, 16 biases here, 16 neurons, 16 biases here, 10 neurons, 10 biases here. These are the number of parameters this neural network will have. So while training this neural network, these many parameters has to be optimized. We have to find out the best values of these many 13,002 weights and biases. So I'm just skipping the part. Now coming to deep learning, as Dr. Satendra must have told you in the morning itself, it's deep learning is more about representation learning. It's more about extracting features. In traditional machine learning, we had handcrafted features. So why not we have certain mechanism where we can learn the features from the data itself? Because the features plays a crucial role while solving any of these problems. So why can't we learn the hierarchy of the features directly from the data instead of handcrafting the features? So that is how the deep learning came into existence. So deep learning is also known as representation learning. And the main objective of deep learning is to learn rich hierarchical representation of the features automatically through multiple stages of feature learning process. What does it mean? As I told you, these hidden layers, larger number of layers are responsible for extracting important information out of the input data. And that is how deep learning helps us in extracting features automatically from the data. Now, what we have seen just now is you have dense network in the case of these neural network for image classification. You have seen here, let me go back to that slide. These are dense network. Each of the input neuron is connected to all the neuron in the hidden layer. That means that many parameters here to learn, which makes it a dense network, which increases the number of parameters, which increases the computation for training, right? So consider an example. Earlier we considered only 28 cross 28 dimension image. What if we have an image of 256 cross 256 cross 3? And there are thousands of classes instead of 10. If we use a densely connected neural network, there will be billions of parameters of connections which we have to learn, which makes it very computationally intensive. So what's the idea? There are too many weights actually. There is dense connection between the input layer and the subsequent hidden layers. So there will be too many weights. Why can't we have sparse connections? Why can't we have fewer weights? And the assumption is, if we talk about an image, the nearby areas in an image are related to each other. And the areas which are far off, they are not related to each other. We'll see this assumption, how it helps us. So instead of having this kind of dense connections, we can have convolutions. We can compute the weighted sum of small areas of the image. And thus we can have sparse connections. We'll see. We'll take an example here. The idea is use convolutions instead of dense connections. You must all have studied convolution in signal processing, where we use convolution operation for applying a filter on the signal. So basically, we are doing convolving the filter to pass on certain information of the signal. In the similar manner, we are doing convolution here on the image. We are taking certain filters. Those filters extract some information to pass on to the subsequent layers. That is how it works. In briefly explain this. Yes, we'll do more discussion on this. I have a query here. We'll do more discussion here in the subsequent slides. Don't worry. So in fully connected layer, you can see they are densely connected. That means there are large number of weights and biases here. We need to reduce them. And how we are reducing them? With the help of convolution operation. So basically we are learning features. What is the idea here is, we take this filter, let's say this is 5 cross 5 filter. This 5 cross 5 filter aggregates this information. This is convolved over these pixels and compute a single value here. Similarly, then we can slide this filter to the next pixels and compute the next value. So basically connect patch in the input layer to a single neuron in the subsequent layer. However, in the case of fully connected layer, what we were doing, we were connecting each of the input to the subsequent neuron in the hidden layer. We'll have a detailed explanation here. Please have patience. We'll have a detailed mathematical or graphical representation of convolution. I'll explain in the subsequent slides. Just please have some patience, please. Now, what we are doing here is, we are applying a filter on a patch. What does it mean? Suppose you are given with an image, you apply a certain filter, and filter is nothing but a matrix. Let's say it's a 2D matrix of suppose size 3 cross 3 or 4 cross 4, and the values of these matrix of the filter are basically the weights. And then this filter is shifted all across this image, and subsequent features are computed with the help of these filters. And we can use multiple filters to extract different features. Let me show you this particular operation, how convolution works. Suppose this is the input A, B, C, D, E, F. Consider this as an image, and this is the filter. We also call it kernel. So how do we perform the convolution operation? You do the element-wise multiplication and then do the aggregation. This kernel, these elements of these kernels are nothing but they are the weights. So now you have analogy with that neural network where you are multiplying these weights with these pixel values and then aggregating this information. Aggregation, this you are computing a linear weighted combination where you are multiplying these weights with individual pixel values. This is the output. So basically, this kernel applied over these 4 pixels will yield this linear weighted combination. Similarly, you can slide it here and compute the output corresponding to the next patch and so on. And finally, you get this output. So this kernel is being slid all across this image, and then you are computing this output. This output is nothing but an important information being extracted from this input image. You can consider this as a features map of this input image. This is one of the examples. Suppose this is the input image and this is your filter. This is nothing but an identical filter, or sorry, not the identical, this is the blurring filter. So if you apply this filter over here, you will get a blur version of this image. This is another filter which you can apply here, and you can sharpen this image. So this is special type of filter which sharps the edges of this image. So you can use different kind of filters to extract different information. This is just a convolution operation which I am demonstrating here. This filter is an edge detection filter from the images, which is extracting edges. Now, how do we do the convolution? So this filter being convolved all across this image, we slide this filter all across the image, and then we get one output corresponding to one convolution operation of this filter on a patch. So we just slide the kernel over the input image. Each time we slide the kernel, we get one value in the output, and so on. And similarly, we can use multiple features to have multiple feature maps. So this output which we are getting from this image is nothing but the features of this image. And it depends what kind of feature, it depends on what kind of filter you are using here. If you want to compute more type of features, you can use more filters here. This is another example. Suppose the image is 3D, you have RGB, red, green, blue channels. Now, how do you apply a 3D filter over it? So it's a volume kind of view you can see here. So there are three channels in this image. Similarly, we'll have three channels in the filter. Each of the channel will be convolved with each of the channel in the image, and as a resultant, we'll get a 2D output, which is a feature map. So basically, we are sliding this filter across the length and the width. However, we are not sliding with respect to the depth. The depth of this filter is equal to the depth of this image. So it's three-dimensional filter, which is being convolved with this three-dimensional image because it's a colored one. And as a result, you will get a 2D output. So we are doing a 2D convolution operation on this 3D input because the filter moves along the height and the width, but not the depth. Now, as I was telling you, we can apply multiple filters to have such 2D multiple feature maps. Now, while applying these filters on an image, we face certain issues on the edges of these images. So with the help of padding, we can solve that particular problem. What we have to do is we have to add extra pixels on the edges of the image, and we can do this zero padding on the image so that we get a correct size of the feature map. Now, another one is the stride. As I was telling you, we have to convolve this filter all across this image. So how many pixels we move these filters in the subsequent iteration, that is called as stride. So it defines the interval at which the filter is being applied. So in this case, suppose we are considering the stride as 2, so it will move 2 pixels at a time. So that will basically decide what is the output dimension of this feature. And you can see here the stride, we are moving 2 pixels at a time, and that is called as the stride. You can see this is the example. So now the output dimension of the feature map by after applying the convolution operation is given here. W2 is the width of this feature map. Height is the height of this feature map. W1 and H1 is the width and the height of this input image. F is the dimension of the filter. Suppose this is 3 cross 3, so F is 3. And P is the padding. So if we are doing padding on the edges, then that gives us the value of P. In this case, the padding is 1 here. S is basically the stride. So stride is 2 in this case. So with this formula, we can compute the output dimension of the feature map, that is W2 and H2. This depends on what stride we are using, what kind of padding we are using, and what is the dimension of the filter. Now, as I was telling you, the convolution, the 3D convolution gives you a 2D output. And now suppose if you want to apply k such filters, so basically you will get k dimensional, the depth of the output will be k. So if you are using only one filter, one three-dimensional filter, you will use only, you will get the depth as 1. However, if you are using k such three-dimensional filters, you will have output depth as k, and the width and height is given with the help of the same formula which we have discussed. Now, what is the main difference here? Classification using the feed-forward neural network and image classification using the convolutional neural network. You have seen here in the case of feed-forward neural network, you have dense connections. This is the regular feed-forward neural network which we have seen earlier. There are many dense connections here. So for computing this particular H11 here, you will have these 16 inputs and the corresponding 16 weights. However, in the case of convolution, it will be different. In the case of convolution, suppose this is the 4 cross 4 image in which this particular is the digit. Now what we will do, we will apply a convolution operation on this 4 cross 4 input. Only few neurons will participate in the computation of that activation H11. In this case, these 4 neurons will participate. Hence, there will be only 4 weights which will be multiplied with these corresponding inputs. So this H11 for these 4 pixels inputs are contributing for the computation of this H11. Similarly, for H12, only these 4 pixels are contributing. And for H13, these 4 pixels are contributing. Now, try to visualize it here. We are using a common filter which is being applied all across this image. That means the weights are same. Those 4 weights are same whether the filter is applied here or the filter is applied here or here. That means we are not using different weights in contrast to the feed-forward neural network where we had different weights for each of the input. Here we are using same weights irrespective of the location of the pixels. So now the connections are sparse and we are taking advantage of the structure of the image. So interactions between the neighboring pixels are more interesting here. That's how we are having the sparse connectivity, which in turn reduces the number of parameters in contrast to the feed-forward neural network where we have dense connections. And another advantage of convolutional neural network or deep neural network is the weight sharing mechanism. Consider this particular network here. Suppose we are applying kernel 1 and kernel 2. There are 2 filters, filter 1 and filter 2. Now, as I was telling you, this filter will be convolved all across the image. It will be slided all across the image. That means the same filter will be applied all across the image. That means the weights will be same. It means we are sharing the weights. The weights are being shared all across this image. You can see the depiction here. This is what we are doing. All these weights are same. Now, if we apply different kind of filters, definitely the weights will be different. So, if we are using only one filter in the convolution layer, the weights will remain same for the whole image. We will not have different weights for different location of the image. That concept is called as weight sharing. Now, if we are using multiple features for extracting multiple filters for extracting multiple features, we'll use different weights in those filters. Okay. Now, this is one of the typical example of convolutional neural network. It has an alternate convolution and pooling layers. Convolution layer, I have already told you what exactly it does. We apply different filters on the input image to extract feature maps, and we use multiple filters to have multiple feature maps in the convolution layer. And then we have pooling layer to reduce the dimension. This is another depiction of convolutional neural network. So the convolution neural network comes along with the activation layer. So the convolution basically computes the linear weighted combination, and that pre-activation goes through the activation function to go to the subsequent layers. Now, convolution layer, convolution with multiple filters, and what will be the output? Output will be the feature map, and what will be the dimension? Dimension will be dependent on the number of filters which we are applying here. Coming to the pooling layer, the task of the pooling layer is to reduce the dimension, and also it gives you invariance to transformation of rotation and translation. I mean, it maintains the spatial integrity of the image. As in this example here, you can see that we are only reducing the dimension of the input feature map with the help of pooling. However, the spatial structure of the data remains intact. So there could be, let us see graphically how pooling works. This is the input. This is the filter which is being applied over it in the convolution layer. This is what we get as the output. Suppose these are the pixel values or the values in the feature map. Now, if we are applying a max pooling, and the dimension of the max pooling is 2 cross 2 with a stride of 2, then we get this kind of output. So basically what we do is in max pooling, we find out the max value in this 2 cross 2 dimension, which is 8, and then we shift this filter by stride 2. So basically, we are doing max pooling in 2 cross 2 dimension, and since the name max pooling, we are finding the max value and we are passing this max value to the subsequent layer. Similarly, in this particular region, 5 is the maximum value. That's why the max pool filter gives you 5 as output. In this example, where we have stride 1, so definitely if the stride is 1, the dimension will be higher in comparison with dimension given by stride as 2. So instead of max pooling, we can also do average pooling for these particular filter dimensions. Now, of course, the activation function rectified linear unit. After applying each of the convolution operation, definitely we apply an activation function which gives us nonlinearity into the model. So this is one of the typical example here. In this case, if we apply rectified linear unit on this particular feature map of the output of the convolution, we'll get this as an output of activation. And the function for rectified linear unit is max of 0 and x, which is being shown with this particular graph. Now, as you have seen in this particular, go back to slide here, the initial layers are convolution and pooling layer. Once we come up at a stage where we have extracted the meaningful information in a lower dimensional space, next task is to flatten the information which is in 3D, we make it, we vectorize it, and then we apply certain mechanism to classify these features. So the next layer is basically the flattened layer or the fully connected layer. The standard neural network where every input neuron connects to every output neuron. Often it is used from to migrate from the image feature map to the final output or map the image feature to a single vector, because there we have to decide which class these input or these features belongs to. And of course, here we are eliminating the spatial information because this is no more needed. We are just interested in the values of these neurons. That is how the representation looks like. The initial layer convolution layer extracts the edges, lines, corners, and then slowly they are being aggregated, and finally at the subsequent layers, the meaningful information are being extracted or clubbed together to have rich hierarchy of the features. This is one of the typical case study of digit classification with the help of convolutional neural network. LeNet, which was proposed in 1998, which was considered as first of the convolutional neural network for image classification. In the practical session today, we will implement convolutional neural network for digit classification. This was just the depiction of LeNet, which was used for digit classification. These are the parameters. What stride was used, what dimension of the filters was used, how many filters were used, what kind of padding was used, and this gives you total number of parameters for each of the layers which are being used. I'm just skipping this part because we will be considering this in the practical session scheduled later in the day today. How do we train the CNN? So training the CNN is similar to how we are training our feed-forward neural network. So basically, the CNN can be implemented as a feed-forward neural network. Only difference is only few weights are contributing here, or only few weights are active here. However, in the case of that feed-forward neural network, all the weights were activated. So now what we can do here is we can compute those gradients with respect to these weights which are active only. So you can imagine we have lesser number of weights for which the network has to be trained. The similar mechanism will be used here. So we will train this convolutional neural network using the same back propagation algorithm, thinking of it as a feed-forward neural network with specifically with sparse connections. So I think there is a lot to discuss, but we are running out of time. I have tried to give you the basic idea of these deep neural networks. Now, if you have any queries, please let me know quickly. We can have quick queries, or maybe if I'm sure everybody must be hungry for lunch because we are late for lunch. Let's have a break, and then we can have queries related to this particular session in the subsequent practical session, which we'll have after lunch. I think one question, can you share the PPT? Definitely we'll be sharing the PPT. Is there any tool for implementation? Yes, we'll have a practical session in the subsequent and after lunch, where I'll be demonstrating how do we implement this convolutional neural network. So we'll have a detailed analysis at that time. Fine. So I guess let's meet at 2:30.
Yes, 2:30 we can start next session.
Yeah. So we'll be discussing the introduction to TensorFlow, and we'll be implementing a convolutional neural network for digit classification in the subsequent practical session. Also, we'll take queries. Any queries you have, please make a note, and we'll have discussion in the subsequent.
So regarding the PPT, it will be available on the canvas towards the end of the day. All the session PPTs as well as YouTube links of the lecture will be available in the canvas towards the end. So do register if you have not registered on the canvas. And regarding the question about convolution, I think in the second half, after the lunch, the question can be continued. Just to give you a rough idea. So convolution is basically mathematical operation. So term convolution means a mathematical operation between two matrices that gives you a single output. And other details you can ask with the sir in the next session. So join by 2:25. We'll start our next session at 2:30 sharp. Thank you.